Greetings, tech enthusiasts. Today, we're going on a mind-bending journey to explore the dimensions of the universe. Get ready to wrap your head around mind-boggling concepts and theories as we delve into the deepest corners of space and time. From the smallest particles to the largest structures in the cosmos, we'll take you on a ride that will challenge your understanding of the universe we live in. So, buckle up and join us as we explore the mysteries of the universe in all its dimensions. And don't forget to watch till the end, because we've got some mind-blowing surprises in store for you. Dimensions, the stuff of math nightmares and sci-fi dreams. But fear not, dear viewers, for today we're going to demystify the concept of dimensions in the context of the universe. First off, what the heck are dimensions, anyway? Well, simply put, they're the different directions in which things can move or exist. In the context of the universe, we're talking about the dimensions that make up space and time. Now, you might be thinking, I thought there were only 3 dimensions: length, width, and height. Fellow techies, that's where things get interesting. You see, those 3 dimensions are what we call spatial dimensions, but there's another dimension that we're all familiar with: time. So, in this video, we'll be exploring the 4 dimensions of space-time that we know and love, and we'll also dip our toes into the mind-bending theories that propose additional dimensions beyond our understanding. Get ready to expand your mind and buckle up for a journey through the wild and wacky world of dimensions. The zeroth dimension, a dimension so elusive, some might say it doesn't even exist. But exist it does, in the world of mathematics and physics, and it's a fundamental concept that lays the groundwork for our understanding of the universe. So, what exactly is the zeroth dimension? Simply put, it's a point, a location in space that has no length, width, or height. It's the most basic building block of geometry, and it serves as the foundation for all other dimensions. In the context of physics, the zeroth dimension is often used to represent point particles, particles that have no size or shape, but still possess mass and energy. These particles are so tiny that they're practically impossible to observe directly, but they play a crucial role in our understanding of the universe. For example, the zeroth dimension is used in quantum mechanics to represent the position of a particle at a given point in time. By analyzing the probability distribution of where a particle might be located, scientists can make predictions about its behavior and interactions with other particles. Additionally, the zeroth dimension is used in mathematical models of string theory, which propose that particles are actually tiny one-dimensional strings that vibrate at different frequencies. By studying the behavior of these strings in different dimensions, scientists hope to gain a deeper understanding of the fundamental forces of the universe. Moving up from the zeroth dimension, we arrive at the first dimension, a dimension that introduces the concept of length and direction. In this dimension, objects can move only along a straight line, without the ability to move in any other direction. In the context of geometry, the first dimension is represented by a line, a collection of points that extend infinitely in 2 opposite directions. This line has no width or depth, only length, and it serves as the basis for all other one-dimensional shapes, such as line segments and rays. In physics, the first dimension is used to describe the position of an object along a line. By measuring the distance that an object has traveled in a certain direction, scientists can determine its position in the first dimension. This can be used to track the movement of objects, as well as to make predictions about their future behavior. For example, in the field of mechanics, the first dimension is used to describe the motion of objects under the influence of forces. By analyzing the position, velocity, and acceleration of an object in the first dimension, scientists can make predictions about how it will move and interact with other objects in its environment. Additionally, the first dimension is used in mathematical models of wave behavior, such as sound and light waves. In these models, the first dimension represents the length of the wave, and the amplitude of the wave is represented by the height of the wave above or below the zero line. As we move up from the first dimension, we arrive at the second dimension, a dimension that introduces the concept of width and depth. In this dimension, objects can move along a flat surface, but they cannot move in any other direction. In the context of geometry, the second dimension is represented by a plane, a flat surface that extends infinitely in 2 directions. This surface has no thickness, only width and height, and it serves as the basis for all other 2-dimensional shapes, such as rectangles, triangles, and circles. In physics, the second dimension is used to describe the position and movement of objects on a flat surface. This can be used to track the movement of objects in a 2-dimensional space, as well as to make predictions about their future behavior. For example, in the field of optics, the second dimension is used to describe the behavior of light waves as they move through a two-dimensional surface, such as a lens. By analyzing the properties of light waves in the second dimension, scientists can create mathematical models that accurately predict the behavior of light and its interaction with matter. Additionally, the second dimension is used in the study of fluid dynamics, which involves the motion of fluids such as water and air. By analyzing the movement of fluids in two-dimensional planes, scientists can create models that accurately predict the behavior of fluids in three-dimensional space. Moving up from the second dimension, we arrive at the third dimension, a dimension that introduces the concept of depth and volume. In this dimension, objects can move in any direction in three-dimensional space, allowing for a much richer and complex understanding of the universe. In the context of geometry, the third dimension is represented by a solid object, a shape that has length, width, and height. This object can occupy a certain volume of space, and it serves as the basis for all other three-dimensional shapes, such as cubes, spheres, and pyramids. In physics, the third dimension is used to describe the position and movement of objects in three-dimensional space. By measuring the volume that an object occupies in the third dimension, scientists can determine its position and motion within that space. For example, in the field of astronomy, the third dimension is used to describe the location and movement of celestial bodies in our galaxy and beyond. By analyzing the position and motion of stars and planets in three-dimensional space, scientists can create models that accurately predict the behavior of these objects over time. Additionally, the third dimension is used in the study of materials science, which involves the behavior of materials such as metals, ceramics, and polymers. By analyzing the structure of materials in three-dimensional space, scientists can create models that accurately predict their properties and behavior under different conditions. Moving beyond the third dimension, we enter the realm of higher dimensions, the fourth and fifth dimensions. While these dimensions are not directly observable in our everyday experience, they are essential to our understanding of the universe and its properties. The fourth dimension is often referred to as time, a concept that is intimately tied to our experience of the universe. In this dimension, objects can move not only in three-dimensional space, but also through time, allowing for a much richer and complex understanding of the behavior of the physical world. In physics, the fourth dimension is used to describe the behavior of particles and objects over time. By measuring the position and motion of objects in three-dimensional space at different points in time, scientists can create models that accurately predict the behavior of these objects over time. The fifth dimension is a more abstract concept that has been proposed in various scientific theories, including string theory and M-theory. In these theories, the fifth dimension is often described as a space that is orthogonal to the four dimensions of spacetime. In physics, the fifth dimension is used to describe the behavior of particles and objects that cannot be explained by the laws of classical physics. By introducing the concept of higher dimensions, scientists can create models that accurately predict the behavior of particles and objects in more complex systems. One example of the use of the fifth dimension is in the study of black holes. According to some theories, black holes could be described as objects that exist in higher dimensions beyond our four-dimensional spacetime. By using the concept of the fifth dimension, scientists can create models that accurately predict the behavior of black holes and their interaction with the rest of the universe. The sixth dimension would reveal a plane of potential worlds, where all the possible universes that begin with the same initial conditions as ours, i.e. the Big Bang, can be compared and positioned. By mastering the fifth and sixth dimensions, it could theoretically enable time travel or traveling to alternate futures. Moving on to the seventh dimension, it provides access to possible worlds that originate with different initial conditions. Unlike the fifth and sixth dimensions, where the initial conditions were identical, in this dimension, everything is different from the outset of time. The eighth dimension showcases a plane of such potential universe histories, each starting with distinct initial conditions and branching out infinitely, hence the term, infinities. In the ninth dimension, we can compare all the potential universe histories, each starting with different laws of physics and initial conditions. In the 10th and final dimension, everything that is conceivable and possible is encompassed. These 6 additional dimensions are crucial to string theory to ensure consistency in nature. We can only perceive 4 dimensions of space, and this can be explained in 2 ways. Either the extra dimensions are compactified on a small scale, or our world resides on a 3-dimensional submanifold corresponding to a brane, where all known particles except gravity are limited. And there you have it, folks. We've just taken a journey through the mysterious and mind-boggling dimensions of the universe. From the 0th dimension all the way to the 10th, we've explored the possibilities of space and time. I hope this video has opened up your mind to the vastness of the universe and made you wonder what else could be out there beyond our limited perception. Who knows, maybe one day we'll be able to master the dimensions beyond our own and unlock the secrets of the cosmos. Until then, keep exploring and keep learning. And don't forget to hit that subscribe button to stay tuned for more mind-bending content on Tech Nation.